Hi, this is Alex from devstories.eu. LangGraph, episode 3 of 18. Two parallel functions finish executing at the exact same millisecond and try to write to the exact same shared list. Usually, one overwrites the other and data vanishes. To prevent this, LangGraph relies on the Graph API, state, and reducers. The foundation of any LangGraph workflow is its state. You define this using a standard Python TypedDict. This dictionary lays out the exact keys your graph will track and the data types for each key. Think of it as the schema that gets passed from node to node as your graph runs. Here is the key insight. Nodes in LangGraph do not mutate the state directly. A node receives a copy of the current state, does its work, and returns a dictionary of updates. A common mistake is assuming that returning a dictionary replaces the entire state object. It does not. If your state has 5 keys and your node returns a dictionary with just 1 key, LangGraph leaves the other 4 untouched and only applies your specific update. How does LangGraph apply that update? That is where reducers come in. A reducer is simply a function that dictates how a returned value merges with the existing value for a specific key. By default, LangGraph uses an overwrite reducer. If your node returns a new string for a status key, the old string is gone, replaced entirely by the new one. Sometimes, overwriting is exactly what you want to avoid. Consider a parallel data fetching workflow. You have a shared state key called results, which is a list. You spin up 2 nodes running at the same time to fetch different batches of data. If both nodes return a dictionary updating the results key, the default overwrite behavior causes whichever node finishes last to erase the other's work. To fix this, you annotate the results key in your TypedDict with a specific reducer, like Python's built-in operator .add. Now, when the 2 nodes return their lists, the reducer acts as a trophic cop. It takes the existing list and safely appends the outputs from both nodes. Nothing gets dropped. There is one edge case. What if you have an append-style reducer on your results key, but you reach a point in your graph where you genuinely need to wipe the list clean and start over? If your node returns an empty list, the reducer just adds an empty list to the existing one, leaving the old data intact. For this scenario, LangGraph provides a special overwrite type. When your node wraps its update in an overwrite object, LangGraph detects it and bypasses the reducer entirely. It throws away the old list and forces a hard reset. State in a complex graph is not a fragile global variable being constantly mutated, but an append-only log of controlled updates governed by clear reduction rules. That's all for this one. Thanks for listening and keep building.